Few machines in history have pushed the boundaries of engineering like the SR-71 Blackbird, a jet so advanced it could cruise at over 3 times the speed of sound while flying high enough for its pilots to see the curvature of Earth. From its futuristic design to its ingenious hybrid propulsion system, the SR-71 wasn't just ahead of its time, it defied it. Let's dive into how this long-range reconnaissance aircraft shattered the limits of speed, altitude, and endurance, while making sure no enemy could touch it. The mission: fly higher, faster, farther. At an operational ceiling of around 26 kilometers, 85,000 feet, the SR-71 flew where the sky turns dark and the thin atmosphere reveals the black of space. Cruising at Mach 3.2, about 3,540 km per hour, it could cover a mile every 1.6 seconds. When radar detected a surface-to-air missile launch, the Blackbird's countermeasure was elegantly simple: accelerate and turn slightly. Even though many missiles had a higher peak speed, none could match its sustained velocity, range, and agility at extreme altitude. Across hundreds of missions over hotspots like Vietnam, North Korea, and Iraq, not a single SR-71 was ever lost to enemy fire, despite countless attempts. Engines from another world. At the core of the SR-71 Blackbird was the Pratt & Whitney J58 turbojet, an engine so unconventional that in its unmodified state it could only provide around 17.6% of the thrust needed to sustain Mach 3.2. The secret to overcoming this shortfall was its ingenious turbojet-ramjet hybrid design. A conventional turbojet uses spinning compressor blades to draw in air, compress it, mix it with fuel, and ignite the mixture, ideal for subsonic and low supersonic flight, but unable to handle supersonic airflow at the inlet efficiently. A ramjet, on the other hand, thrives at extreme speeds by compressing incoming air purely through the aircraft's forward motion before combustion, with no moving parts involved. The drawback is that it cannot operate from a standstill and requires another propulsion system to get up to speed. The SR-71 solved this by seamlessly transitioning between the two modes. Below Mach 2, it acted mostly as a turbojet, but as velocity increased, more airflow bypassed the turbojet core, allowing it to operate increasingly like a ramjet, producing the enormous thrust needed for sustained Mach 3+ flight. The secret: airflow management. The J58 engine lived inside a carefully engineered nacelle surrounded by ducts, bypass channels, and movable parts that sculpted the airflow. The most famous of these was the inlet spike, a pointed cone capable of sliding backward by up to 0.66 meters. Up to Mach 1.6, the spike stayed forward. Beyond that, it retracted slightly, about 41 mm for every 0.1 Mach increase, to keep a supersonic shockwave parked at the perfect spot in front of the compressor, critical for efficiency. Perforations in the spike let slow-moving boundary layer air bleed away, freeing more space for high-energy airflow. Surrounding the engine was a bypass area that redirected excess air around the turbojet. This cooled the engine and, after rejoining the exhaust stream behind the afterburner, provided extra thrust. Multiple bypass door systems, forward, aft, and suck-in doors, kept the inlet pressure stable. Mismanaging them could cause the shockwave to spill out, triggering a violent event called an unstart, which would jerk the plane sideways and cause sudden loss of thrust. The afterburner transformation. The SR-71's 6 compressor bypass ducts were the real magic. At high speed, they dumped air directly into the afterburner, bypassing the core engine entirely. This allowed the J58 to behave less like a turbojet and more like a ramjet, generating the massive thrust needed for Mach 3+ cruise. Afterburners work by injecting fuel into the jet exhaust and igniting it, using leftover oxygen to create an extra pressure surge. Normally inefficient, they became far more effective at high speed, where ram compression replaced the need for heavy compressor work. The fuel challenge. Given its enormous fuel appetite, you might think the Blackbird's top speed was limited by fuel consumption. It wasn't, but fuel was still a monumental engineering challenge. The SR-71 carried 59% of its takeoff weight in fuel, roughly 36 tons when full. It had no internal weapon bays, so much of its fuselage space became fuel storage. Why it leaked on the ground. Instead of separate tanks, the SR-71 used a wet wing system, storing fuel directly inside the titanium skin cavities. This saved weight, but titanium expanded in flight and contracted on the ground, opening tiny gaps in the sealant. Fuel leaks on the runway were a fact of life, and maintenance crews could only minimize them, not eliminate them. Aerial refueling. Without mid-air refueling, the SR-71's average range was around 5,200 kilometers, about a one-way trip from New York to London. At high temperatures, the climb from Mach 1.25 at 30,000 feet to Mach 3 at 70,000 feet could burn 36% of the total fuel load. Cooler ambient air nearly halved that figure. With tankers in the sky, the range became almost limitless, restricted only by crew endurance and mechanical reliability. The longest mission on record lasted 11.2 hours in 1987, involving at least 5 refuelings during a flight from Okinawa to monitor the Iran-Iraq War. The real speed limit, heat. The ultimate limitation on the SR-71's performance wasn't fuel or thrust, it was heat. At its sustained cruise speed of Mach 3.2, the nose of the aircraft reached temperatures of roughly 300 degrees Celsius. The front sections of the engine nacelles heated to around 306 degrees Celsius, and the rear of the nacelles soared to an intense 649 degrees Celsius. At higher speeds, these temperatures would climb even further, pushing the structural materials toward their limits. Even titanium, chosen for its exceptional heat resistance, would begin to lose strength if pushed much beyond this point, making temperature the true ceiling for the Blackbird's incredible speed. Special fuel for a special plane. The SR-71 ran on JP7, a custom fuel with a high flash point and very low volatility. It wouldn't evaporate easily, ignite accidentally, or vaporize in the tanks at high heat. JP7 was so stable that it could be pumped through the airframe as coolant for hydraulic systems, engine oil, and avionics before being sent to the combustion chambers. It was so hard to ignite that the aircraft carried 𝐼𝐵𝐷, a chemical that bursts into flame on contact with air. Each engine start and afterburner ignition required a precise 𝐼𝐵𝐷 shot, with only about 16 available per mission. Why black? Airliners are white to reflect heat, so why was the SR-71 painted jet black? At its high speeds, heat came mainly from aerodynamic friction, not sunlight. Here's where Kirchhoff's law of thermal radiation comes in. Good absorbers are also good emitters. The black paint allowed the SR-71 to radiate heat away more effectively than bare metal or lighter colors, critical for keeping temperatures in check. Titanium, the metal that made it possible. Aircraft of the era relied on aluminum for its low weight, strength, and machinability, but aluminum loses strength above approximately 150 degrees Celsius. The Blackbird's skin regularly endured twice that temperature. The answer was titanium, which makes up 93% of the SR-71's structure. It's strong, lightweight, and retains most of its strength up to around 600 degrees Celsius. Titanium's low thermal expansion also reduced stress from heating and cooling cycles. However, titanium is notoriously hard to work with. It reacts with oxygen during welding, is expensive to refine, and wears down machining tools quickly. Building the SR-71 required entirely new fabrication methods. Ahead of its time, then and now, the SR-71 even incorporated early heat-resistant composite panels in non-structural locations to reduce radar signature. At the time, composites couldn't handle heavy structural loads, but today they can. Its conceptual successor, the SR-72, is in development and may be capable of Mach 6. Advances in composites, 3D printed titanium parts with built-in cooling channels, and autonomous control mean it could fly faster, farther, and without a pilot on board. A legacy of impossible engineering. From its hybrid propulsion and thermal management to its stealthy design choices, the SR-71 remains one of the greatest feats in aerospace history. It was a machine that turned heat into an enemy and then into an ally, that transformed a leaking fuel system into a necessary compromise, and that rendered missiles obsolete through sheer speed and altitude. Even decades after its retirement, engineers still study the Blackbird, not just to learn how it worked, but to marvel at the audacity of those who dared to build it. And that's the story of the SR-71 Blackbird, the spy plane that could outrun anything in the sky. If you enjoyed diving into the engineering behind this marvel, give this video a like. It really helps the channel grow. Got thoughts or questions? Drop them in the comments. I read them all. For more deep dives into legendary aircraft and groundbreaking tech, subscribe and ring that bell so you don't miss the next one. Thanks for watching, and I'll see you in the next flight.